Hey, this is a video on integration by trigonometric substitution. So, last week we learned about integration by parts, and I know it's difficult, but it was very useful at doing certain types of integrals that we could not complete in any other way. So integration by trigonometric substitution is also quite challenging, but it's also very useful for specific types of integrals that cannot be evaluated any other way. Okay, so it's a challenging topic, but it's very important. And the basic idea is you're going to let your u actually equal some number times a trig function. So for example, you can have u equals a tangent of theta, u equals a sine of theta, or u equals a secant of theta. So there's actually three different forms there. Number 1, number 2, and number 3. And these are actually in your formula sheet, the same formula sheet that I always refer to in my videos. If you go to there on the second page, you're going to see in the middle of the second page it says Trig Substitution, and they've got a triangle drawn there. It's a right triangle, and then they have this information here that I have on my whiteboard. Okay, so what we're going to be doing here is we're going to, when you're trying to do an integral and you get something in one of these three forms here, so let me circle them in blue. If you get it in any of those forms, that's where you want to make a trig substitution. Okay? So if your integral contains any one of those forms, so if integral contains one of these forms that I circled in blue, use trig substitution. Use trig substitution, trigonometric substitution. And don't get this confused with u substitution. I know they're using u here, but it's a different kind of substitution, because in u substitution you let u equal something and then you find du, right? Well, here we're actually letting u equal something times a trigonometric function, so it works a bit differently. And an example is worth 1,000 words, so we're going to do one in just a second. Now this triangle that I drew here is an example of a right triangle. This one would actually be the one for number 1. So if you say u equals a tangent of theta, this is actually going to be triangle number 1 that I have drawn here. Okay, because if you think about it, if you have u equals a tangent of theta, then that means that tangent of theta actually equals u over a. If I divide both sides by a, I get tangent of theta equals u over a. And remember that tangent of theta is the same as opposite over adjacent from SOHCAHTOA. So, so here the opposite is going to be u, and then the adjacent is going to be a. Okay, so opposite is u, adjacent is a. And then if you use the Pythagorean theorem, we know that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. In other words, this hypotenuse has to be the square root of u squared plus a squared. And that's how we get this form here. And notice that this form here, I labeled it as number 1. That's exactly what I was showing you over here. And I'm not going to write down triangles for all three different forms because it's just too time consuming. I want to actually get into some examples. But basically, if your integral contains one of these three forms, either square root of a squared plus u squared, square root of a squared minus u squared, or square root of u squared minus a squared, then you're going to use trig substitution. So you're going to make one of these three substitutions. And the nice thing about the formula sheet is it shows you which one to use in each case. So you don't have to memorize it, and you don't even have to memorize the right triangles, which can be kind of tedious. That being said, it's often good to draw a right triangle anyway, but you don't always have to. It's just in some situations you need a right triangle. Anyway, with these, when you get the square root of a squared plus u squared, that simplifies to a times absolute value of secant of theta. Okay? And, you know, you'll see that when I do an example. You'll see why it simplifies to this. But basically, if you plug in a tangent of theta for u here, you're going to get a squared plus a squared tan squared of theta. And then if you factor out an a squared, you're going to get a 1 plus secant squared on the inside, and then that's going to simplify, a 1 plus tangent squared, and that's going to simplify to secant squared. But you'll see it in an actual example. I'll show you all that in an example. Okay, so let's jump in. Examples are always my favorite part. Okay, so example, for each of these they want to evaluate the integral. Okay, so evaluate the integral. Okay, and for problem number 1, we're going to be doing the integral of dx over the square root of 361 plus x squared. Okay, so the integral of dx over the square root of 361 plus x squared. Now, you can't do this one by parts. You can't do it with any of the other methods we learned. You might be able to do it with hyperbolic functions, but since we're trying to do these integrals by trigonometric substitution to learn about it, let's go ahead and use that here. So I'm going to go ahead and rewrite the 361 as something squared. So the reason I want to do that is looking up here, we need to have one of these three forms, okay? And obviously it's going to be the top one here because that's the only one with a plus. But we're going to need it as something squared plus something else squared under the radical to use this form. Okay, so we're going to need to find the square root of 361. Probably the best way to do that, since it's not in your times tables, is to use a calculator. So what is the square root of 361? Let's see if it's an actual number. It's 19. Let's see, I wouldn't have known that. Okay, so the square root of 361 is 19, which means that 19 squared is 361. Okay, so my first step is to just write it in the format where I can use a trigonometric substitution. Okay, so now we have the integral of dx over the square root of, well, we said 361 was 19 squared plus x squared. Okay, and then we go back up to our formulas, and as I was saying, it's obviously this first one, right? So the substitution we're going to make is u equals a tangent of theta. But here our u, let me circle our u in green. Our u is the variable, so u is the variable here. But in this problem we can see that u is actually x. Okay, so here u is going to equal x, and then a is whatever number you had over here. So here a is going to equal 19. Okay, so a equals 19 and u equals x. And then we're going to go ahead and make the trigonometric substitution. So we're going to use u equals a tangent of theta. Okay. That's called making a trigonometric substitution. So we say let u equal a tangent of theta. But the thing is, in this problem, u is actually just x. Okay, so that's the same as saying x equals, well, a is 19 tangent of theta. Okay, so the u equal a tangent of theta, that's just from the formula sheet. But here we don't really need that. We mostly need it in this form, where we actually have our x and our a. Okay? So we got our x, and then we have 19. And then, so how do we do the rest of the problem? Well, it does get a little confusing. We've introduced a new variable, theta. Okay, and like I said, you don't have to always draw a right triangle, but sometimes it can be nice. And for this one, I'll go ahead and draw a right triangle. So what we're doing here is trigonometric substitution. And you don't have to sketch this right triangle, but I'm going to go ahead and do it just so you can see it. So for this one, since tangent of theta equals x over 19, that's opposite over adjacent. That means that if this is theta here, then the opposite is going to be x, the adjacent is going to be 19, okay? And then the hypotenuse is going to be the square root of x squared plus 19 squared. Okay? So this is going to be our trig substitution. Trigonometric substitution. And you might be wondering, well, why are we bothering to do all this? It seems like a lot of work. Well, it is a lot of work. That's why I said it's a challenging topic. But it is very useful because it allows you to do some integrals that even integration by parts won't do. And of course, you can combine it with other techniques that we've learned as well. Okay, so what we got here is we have an integral, and we can go ahead and plug in x equals 19 tangent of theta, and then you're going to see some magic here. Okay, so plugging in here, we've got the integral of dx over the square root of 19 squared plus 19 tangent of theta, quantity squared. Okay, and then from there we notice that we have a bit of a problem, which is if you look at this integral that I'm trying to do here, we notice that on the bottom we've gotten rid of x, okay, because we did a trigonometric substitution, x equals 19 tangent of theta. So now our variable is theta on the bottom here, but on the top we're still in terms of x, and that's no good. You can't have an integral in terms of more than one variable unless it's a multiple integral, which we haven't even done. Okay, so what we're going to do here is we need to replace this dx with something involving theta. Okay, that's a trick here. So how are we going to replace dx with something involving theta? Well, just like when you're doing u substitution, you have your u equals whatever, and then you find your du equals the derivative of that. Well, here we're going to be doing the same thing except with x. Okay, so what we need is a dx. So if we take this equation here that we use for the trig substitution, we can take the derivative of both sides, and that will give us dx. Okay, so if I take the derivative of both sides, I get dx equals 19 times, well, here we have to do the chain rule. Okay, so we take the derivative of the outer function, which is tangent, and what's the derivative of tangent? Well, remember, it's actually secant squared. And again, if you forget any of these formulas, you can go to derivatives on your first formulas page. ddx of tangent of u equals secant squared of u times du dx. Okay, so that's the formula we're using there. So 19 is a constant, and then the derivative of tangent is secant squared. So that's going to be secant squared of theta. But we still have to use the chain rule. Okay? So what we're actually calculating here is we're calculating dx d theta. That's really what we're doing. But if you use the chain rule here, you just get d theta. So I had it on this side, but we want to really move it to the other side. Okay, so we've got dx equals 19 secant squared of theta d theta. So you can think of that d theta either as being the chain rule, or you can think of it as moving the denominator of dx d theta to the other side. Either way, you should just be taking the derivative, and then you need to have a d theta over here. Okay, and I don't recommend that you solve for d theta, because this is already solved for dx. And what we want to do here is, unlike with u substitution, we want to actually plug in this 19 secant squared of theta d theta, and we're going to be plugging that in up here for dx. Okay, so we're going to go ahead and plug in 19 secant squared of theta d theta for dx. Okay, so we've got the integral of 19 secant squared of theta d theta on the top, and then on the bottom we can simplify what's inside of this radical. So on the inside of this radical, realize that we can distribute the square here for the second term. Okay, so we're going to have 19 squared times tan squared of theta. Alright, so we have the square root of 19 squared plus 19 squared tangent of theta, tan squared of theta. Okay, and then what can we do to simplify this? Well, we can factor out a 19 squared on the bottom inside of the radical. Okay, so if I factor out this 19 squared inside of the radical, I'm going to get, on the bottom we have the square root of 19 squared times the quantity 1 plus tangent squared of theta. And by the way, you don't have to write this many steps. I'm just writing every step so hopefully no one gets lost, so that hopefully everyone who's watching this can understand it. Okay? Okay, and then on the top we still have a 19 secant squared of theta d theta. Alright, so what happens here? Well, you can split up this square root into two parts. So we can write it as the square root of 19 squared as the first part times the square root of 1 plus tangent squared of theta for the second part. So for the square root of 19 squared, the square root and the square cancel, and we just get 19. And then we notice that there's a 19 on the top as well, so those 19s just cancel out. Okay, so what we have here is actually the integral of secant squared of theta d theta all over the square root of 1 plus tangent squared of theta. But remember that 1 plus tangent squared of theta can be replaced with something else using a trigonometric identity. And I believe 1 plus tangent squared of theta is secant squared of theta, but just in case I'm wrong, let's look at our formula sheet. So if we go to the second page of our formula sheet under trigonometry and key trig identities, we have tangent squared of theta plus 1 is secant squared of theta, right there. So I was correct. Okay, so we're going to plug that in for this one that I circled in red. Okay, so what we got here is the integral of secant squared of theta d theta on the top, and then on the bottom we have the square root of secant squared of theta. Okay, so what does that become? Well, once again, the square root and the square are going to cancel. Okay, the square root and the square are going to cancel. So we're just going to have a secant of theta on the bottom. But remember, when you're taking the square root of a square, it doesn't just cancel, you actually get the absolute value of the number. Now when we were doing that with 19, I didn't bother to write the absolute value because 19 is already positive, so we don't care. But down here, because secant of theta is a function and it can be negative, we do have to write the absolute value. Okay, so we have the integral of secant squared of theta d theta on the top, and then on the bottom we have absolute value of secant of theta. Okay, and then something to realize here is that secant squared of theta on the top is actually the same as absolute value of secant of theta squared. And the reason that's true is if you take the absolute value of secant of theta and secant is negative, then it doesn't matter because you're squaring it anyway, so you're going to make it positive anyway. Okay, so the reason I wrote it as absolute value of secant of theta quantity squared is so that I could cancel out with the absolute value of secant of theta on the bottom. And again, the reason I'm allowed to do this on the top is secant squared of theta is already positive because when you square a number, you make it positive. So you're allowed to add in the absolute value and it doesn't change anything. Okay, so now we can cancel out the square and the absolute value of secant of theta on the bottom. So we're actually just going to be integrating absolute value of secant of theta d theta. Now I did do this in a previous video and I kind of waved my arms a little bit about it. So basically what they do on my math lab here is they go ahead and just write it as the integral of secant of theta. And the reason they say they're doing that is they're saying that theta has to be between negative pi over 2 and positive pi over 2. Okay? But that's because we're doing trig substitution. So this is a little different from the arc length problem that I did on the discussion board. But what I'm going to say here is, I'm going to say secant of theta is greater than 0 on the interval negative pi over 2. So when negative pi over 2 is less than or equal to theta, which is less than or equal to pi over 2. Now how do I know this? Well, remember secant is the same as 1 over cosine, and cosine is actually it's actually positive from negative pi over 2 to pi over 2 because it's the x coordinate. Okay, so 1 over a positive number is still a positive number. Okay, and because of that, and you might be wondering, well, how do I know theta is between these two numbers? Well, remember, theta is actually part of a right triangle. Okay, so if we go back up to the triangle that I sketched, theta has to be this angle here, and theta has to necessarily be between negative pi over 2 and positive pi over 2 for it to even make sense. And it actually can't equal negative pi over 2 or positive pi over 2, because if you think about it, then you would actually be at a right angle, and you can't have two right angles in the same triangle. Okay, so theta actually has to be greater than negative pi over 2 and less than positive pi over 2. So this must be true to be a right triangle. And you might be wondering, well, how can you have a negative angle? Well, it just ends up working out that way. You're allowed to have a negative angle, but the absolute value of your angle cannot be larger than 90 degrees, because then you would have two right angles and that wouldn't make sense. Okay, so anyway, when all is said and done, because secant of theta is greater than 0, and I shouldn't have put, sorry, let me erase these. So it's supposed to say less than down here. Negative pi over 2 is less than theta is less than pi over 2. That was a little mistake I made there. Okay, so anyway, because of that, since secant of theta is greater than 0, that means absolute value of secant of theta is the same as secant of theta. Okay, so that was a long way of me explaining it, but it ends up that this is just equal to the integral of secant of theta d theta. And what's the integral of secant of theta d theta? Well, we should know that, and if we don't know it, we can look at our formula sheet. Right here on antiderivatives on the first page, the integral of secant of u du is ln of absolute value of secant of u plus tangent of u, and then of course plus c. So ln of absolute value of secant plus tangent. Okay, but instead of u, here we actually have theta. Okay, so we have ln of absolute value of secant of theta plus tangent of theta plus c. Okay, and this absolute value you can't get rid of, because if you think about it, tangent of theta could actually be negative from negative pi over 2 to pi over 2, because the y-coordinate can be negative if you're in quadrant 4. Okay? So here we leave this absolute value in there, and you might think you're done, but you're not done. Because remember, theta is actually a dummy variable, which means we plugged it in our trig substitution in order to be able to do the problem. But now at the end here, we have to plug back in expressions in terms of the original variable, which was actually x. Okay? So that's going to be our last thing we have to do here. So plug in expressions in terms of the original variable. And here the original variable was x. Okay, you can't leave it in terms of theta, because theta was what we used for our trig substitution. Okay, so if we go back to the beginning, we had x equals 19 tangent of theta. Okay, that was the substitution we made. And now here's the tricky part. What we have to do is we have to actually replace secant of theta and tangent of theta with expressions in terms of x. And this is an example of why the right triangle can actually be really nice, the one that I sketched. Because if we look at, for example, secant of theta, that's going to be 1 over cosine of theta. Okay, and then going back to our original triangle, we know that cosine of theta, using SOHCAHTOA, cosine of theta is adjacent over hypotenuse. So that's going to be 19 over the square root of x squared plus 19 squared. 19 over the square root of x squared plus 19 squared. Where did I get that? Well, that's just going to be the formula from SOHCAHTOA, from trigonometry. So cosine is adjacent over hypotenuse, just like in that picture there. So that's adjacent over hypotenuse. Of course, we don't want cosine, we actually want secant, which is 1 over cosine, which means that secant of theta is going to be 1 over cosine of theta, which just means we flip it over, so now the square root is going to be on the top. So we're going to have the square root of x squared plus 19 squared on the top, and then on the bottom we have 19. Okay, so now we're ready to go ahead and plug this in over at the end of the problem. So secant of theta is the square root of x squared plus 19 squared all over 19. Okay, so we have ln of absolute value of the square root of x squared plus 19 squared all over 19. So that was the secant of theta. Okay, and we probably don't want to leave it as 19 squared, so we're going to go ahead and rewrite it as 361 for the answer. So that took care of secant of theta. And then in blue, let's do tangent of theta. So remember that tangent of theta is opposite over adjacent, SOHCAHTOA. TOA. Okay, so once again, going back to our right triangle, tangent of theta is opposite over adjacent, so it's actually just going to be x over 19. Okay, so tangent of theta equals x over 19, because that's opposite over adjacent for the right triangle I drew. Okay, so opposite over adjacent. Okay, so we're going to go ahead and plug in x over 19 in for tangent of theta. Okay, so we have plus x over 19. And then, of course, we have a plus c at the end because this is an indefinite integral. Should just get in the habit of doing that. Okay? And even though these have the same denominator inside of here, they don't combine them together for whatever reason. So this is how they leave their answer in my math lab. Okay, so that's good. They got the same answer as us, so we did it correctly. Okay, so hopefully that is, I know it took a long time to explain the first one, but hopefully that works out a lot of the kinks of doing these. So now you only have 5 homework problems, but as you can see, one problem took me more than half an hour. So I wanted to go to another problem, and I'm going to choose one that is a little bit trickier for whatever reason. So I probably only have time to do 2 more. So I'm going to do, for this next one, there's just a little trick to it that you might not know. Okay, so for example number 2, we're going to be doing the integral from negative 8 root 3 over 3, negative 8 root 3 over 3, to positive 8 root 3 over 3. Okay, and for our actual integran, what we have here is dx over 64 plus x squared. Okay, so we have the integral of dx over 64 plus x squared from negative 8 root 3 over 3 to positive 8 root 3 over 3. Now the thing is here, you're probably looking at this denominator right now and wondering, well, Mr. Shoemaker, that doesn't look like any of the forms that you gave us. And that's correct, it doesn't. So if we go to our formula sheet under Trig Substitution on the second page, if we look at the 3 forms that I gave you, you have square root of a squared plus u squared, square root of a squared minus u squared, and square root of u squared minus a squared. Well, the problem is, it doesn't look like any of these. But which one does it look the most like? That's the question. I would say it looks the most like the first one because that one has a plus. Something squared plus something else squared. But what about the square root? What can we do about that? Well, that's actually the trick here. So the trick is we can still do a trig substitution because this is something squared plus something else squared. Okay? So what trig substitution are we going to do? Well, we're still going to do the same one we did on the last problem, which is probably quite a surprise to you. So if I rewrite this as the integral of dx over 8 squared plus x squared, because we know 8 times 8 is 64. Then here we can see that if we do the same substitution as last time, our a is going to be 8, and our u is going to be x once again. So a is 8, u is x. So then we do the trig substitution, trig sub, which is going to be the same as the last problem, even though it looks a bit different. So we're going to say u equals a tangent of theta. Okay? So that's going to be x equals 8 tangent of theta. X equals 8 tangent of theta. Okay. You might be wondering, well, how do I know this is going to work? Well, I don't know it's going to work 100%, but it's the closest one that we have. So we're going to roll with it. Okay, so if x equals 8 tangent of theta, then we know that dx is going to equal 8 times secant squared of theta. Okay, and then if we multiply both sides by d theta, this is our dx d theta. If we move d theta to the right side, we get dx equals 8 secant squared of theta d theta. And what I'm doing is I'm just kind of rolling with this, and we'll see how it goes. If this doesn't work, we're going to have to get a little bit more creative. We may have to do a trick here. So, so if we plug the stuff in now, in the numerator we have the integral of 8 secant squared of theta d theta, and in the denominator we have 8 squared plus 8 times tangent of theta quantity squared. So this one looks almost identical to the last one we did. It's just that we don't have a square root in the denominator. Okay, so if you look at your denominator here, we have no square root. So it's not technically in this form, but I'm going with this form because it's almost the same. It's just we're going to somehow have to deal with the fact that we don't have a square root. Okay, but I'm just going to roll with it and see where it takes me. And that's how a lot of things are in STEM. You sort of just roll with it and then, see where you go. Okay? So in the denominator, one thing I can do is I can distribute the square. So we get 8 squared tangent squared of theta. And we know that 8 squared is 64. So we have 8 secant squared of theta d theta in the numerator, and then in the denominator we have 64 plus 64 tangent squared of theta. And then I notice something. I notice that in the denominator I can factor out a 64, kind of similar to the last problem we did. So if I factor out a 64 in the denominator, then I'm going to be left with 1 plus tangent squared of theta. Okay, so I'm left with 1 plus tangent squared of theta in the denominator. Okay, and then I recognize that 1 plus tangent squared of theta is just like the last problem. We said that's the same as secant squared of theta. Okay, so this 1 plus tangent squared of theta is the same as secant squared of theta. That's just one of your trigonometric identities from pre-calculus or trig. Okay, so what we have here is with the 8 and the 64 on the top and the bottom, we can divide those. We can divide the top and the bottom by 8. Okay, so on the top we're just going to have secant squared of theta d theta. And then on the bottom, we're going to have 64 divided by 8, which is 8. Okay, and then also on the bottom, the 1 plus tangent squared of theta becomes secant squared of theta. And here, because we're not doing the square root of a square, we don't have to write the absolute value. The only time you have to write the absolute value is if you have the square root of a square. Okay, but here we just have a square. And the square is automatically an absolute value. That's kind of how it works. So now, for the 8 on the denominator, we can factor that out front. But it's in the denominator, so we're going to actually have a 1/8 outside of the integral. Okay, so we're going to have 1 over 8 times the integral of, well, something happens here. We have a secant squared of theta on the top and the bottom, so those just cross out. So we actually have 1/8 times the integral of d theta. So this problem was a bit confusing at the beginning, but it actually turned out to be a lot easier than the last problem, because even though we didn't have it in the exact form that I say you need to have it in on your formula sheet, we chose the closest form, and we got lucky, and it looks like everything canceled out. So here we only have to integrate d theta, which is very easy to integrate. The integral of d theta is just theta. Okay, so that means we just have 1 over 8 times theta. Okay. Of course, that's not the whole problem. Remember, theta was a dummy variable. We did trig substitution. So now we have to rewrite theta in terms of the original variable x. And also, don't forget, in this problem, it was a definite integral. So at the end, we're going to have to be plugging in x equals 8 root 3 over 3. And also x equals negative 8 root 3 over 3. So we're going to have to plug in the top number and then subtract the function evaluated at the bottom number. Okay, but what we have to do first is we have to rewrite this theta as an expression in terms of x. Okay, so how am I going to do that? Well, like I said, this problem has a couple of tricks. I've already shown you the first trick, which is just choose the closest form and roll with it. You just roll with it and see where it takes you. The other trick is, how do we find theta? Well, there's a lot of different ways of doing it. One thing is, you could draw a right triangle. I never drew a right triangle here. But even with a right triangle, it's not going to tell you what theta is. So what probably most people would do here is they would use this equation here. So let me circle it so you know which one I'm talking about. X equals 8 tangent of theta. So if x equals 8 tangent of theta, that's the same as x over 8 equals tangent of theta. Okay, and then if I apply tan inverse to both sides, I can actually get theta in terms of x. Okay, so I actually get theta equals tan inverse of x over 8. And this isn't the only way you can find theta. You could also draw a right triangle and then do sine inverse or cosine inverse using the right triangle. But I feel like this is the easiest way to do this one because we still haven't had to draw a right triangle. Notice for this one, I didn't even bother to draw a right triangle. And at the end here, I still don't need one. Whereas on the last problem, that right triangle actually came in a lot more handy. Whereas for this one, we didn't need it. Okay, so theta equals tan inverse of x over 8. Okay, so that's what we're going to plug in here. Okay, so tan inverse of x over 8. But of course, we're not going to write a plus c because this was actually a definite integral. And remember, for this definite integral, they wanted us to evaluate it from negative 8 root 3 over 3 to positive 8 root 3 over 3. All right, so remember when you're evaluating an integral, a definite integral, you use the fundamental theorem of calculus part 2, which basically just says you plug in the top number and then you subtract the function evaluated at the bottom number. Okay, so we have 1/8 times tan inverse of, well, the top number was 8 root 3 over 3. So I have 8 root 3 over 3 over 8 minus the function evaluated at the bottom number. So minus tan inverse of 8 root 3 over 3 over 8. And that one's supposed to be negative. I forgot my minus. Excuse me, I forgot my minus. Okay. All right, so quite a bit going on there, but we're almost through to the end. So what we can do here is we can actually cancel out these 8s. Okay, so we have a 1/8 times the quantity tan inverse of, after we cancel out those 8s, we just have tan inverse of root 3 over 3 minus tan inverse of negative root 3 over 3. Okay? Tan inverse of root 3 over 3 minus tan inverse of negative root 3 over 3. Okay, and then how does tan inverse work? Well, you could use, some calculators will do it for you, but most will not give you an exact answer. So what I would recommend for most people is to just use the unit circle that's on our formula sheet. So remember that tangent is the same as sine over cosine. Okay, so tangent of x equals sine of x over cosine of x. Okay, so if we have root 3 over 3, if we look at root 3 over 3, that can be thought of as the same, this is the same as 1 over root 3, which is the same as 1/2 over root 3 over 2. Okay, so what that means is that sine of x is the numerator, which is the same as your y-coordinate, is going to be 1/2. And then the denominator, which is the same as your x-coordinate on the unit circle, is going to be root 3 over 2. Okay, so that means on your unit circle, you're going to have x comma y equals, x is going to be root 3 over 2, and y is going to be 1/2. And so we just really want to figure out what the angle is. And I probably shouldn't have been calling this x, so maybe I'll just call it theta again. Call it theta. Okay, so tangent of theta is sine of theta over cosine of theta. And we're trying to figure out what that theta is. They gave us root 3 over 3. Okay, so we just go on our unit circle. We look for root 3 over 2 comma 1/2. So zooming in here so we can see it. This unit circle. X is root 3 over 2, y is 1/2. So our angle is pi over 6. Okay, pi over 6. So that means tan inverse of root 3 over 3 is pi over 6. Okay, so tan inverse of root 3 over 3 equals pi over 6. All right, so that's what we're going to plug in up here for the tan inverse of root 3 over 3. All right, so what we've got is 1/8 times pi over 6 minus, well, now we have to do tan inverse of negative root 3 over 3. But we can do pretty much the same thing that we did on the other one. So it's going to end up being negative 1/2 over root 3 over 2. So what angle is that going to be? Well, if we look on our unit circle, for the negative root 3 over 3, then that means on our unit circle, I keep saying unit circle, but I don't write it down. Let me write it down. Unit circle, our x comma y is going to be, x is going to be root 3 over 2, and y is going to be 1/2. But in order to be negative, one of those has to be negative. And I believe it has to be the, I believe that the y has to be negative. So I believe it's going to be negative 1/2. Okay? And that has to do with the domain of tan inverse. Okay? So what we got here is root 3 over 2 comma negative 1/2. And that's at 11 pi over 6. Okay? Which is the same as negative pi over 6. Okay? So that means tan inverse of negative root 3 over 3 is either you can write it as 11 pi over 6, or it makes more sense to just write it as negative pi over 6. Okay. Okay. So cool. So we got that. So now we can write the whole thing out. So we've got 1/8 times pi over 6 minus negative pi over 6. And if you remember your unit circle, you wouldn't have to spend this long, going through it. Or if you have a calculator that will just give you an exact answer, those can be very handy as well. But anyway, regardless of what method you use, now these minuses are going to cancel. So we get pi over 6 plus pi over 6, which is 2 pi over 6. So we have 2 pi over 6 times 1/8. And then we can cross out the 2 and the 6, dividing the top and the bottom by 2. Okay, so we actually just get 1/8 times pi over 3, right? Because 6 divided by 2 is 3. And then multiplying straight across, we get 1 times pi is pi, and then on the bottom, 8 times 3 is 24. So we get pi over 24. And that's actually the correct answer, so we're good. So we did it right. Okay? And by the way, if you're wondering why we got a negative pi over 6, it has to do with tan inverse. If you want, you can read up on the domain of tan inverse. I believe it goes from negative pi over 2 to pi over 2, if I'm not mistaken. Okay, so that's why I wrote negative pi over 6. Well, it's technically not the domain, it's technically the range is what I'm referring to. Okay, cool. So, our answer is pi over 24. All right, and then looking at the rest of your homework, most of these are fairly straightforward. But I did want to do one more that looks like the other most challenging problem, similar to the one in your homework. It's not the same, obviously, but it's similar. Okay, so this is going to be example number 3. Okay, so for example number 3, we're doing the integral of the square root of 100 minus t squared dt. Okay, the integral of the square root of 100 minus t squared dt. Now here our variable is t instead of x, but we can still look at the formula sheet on the first page. Let me zoom out. Oh, sorry, the second page, not the first page. Zoom back in. So looking at our formula sheet on the second page under trig substitution, we're looking at these 3 forms and which one looks the most like ours. Well, here once again, instead of u, our variable is actually going to be t this time. So it's in the form square root of a squared minus u squared. So square root of a squared minus u squared is going to be this first trig substitution. Okay, so this is the one we're looking at. So first we need to just rewrite the thing in this form. Okay, so this needs to be in the form square root of a squared minus u squared. Well, here we can see that 100 is 10 squared. So we have the integral of the square root of 10 squared minus t squared dt. Okay, so here a is actually going to equal 10. So a is 10, and then u is t. Okay. So then with that information, we're going to go ahead and make the substitution. So as we can see, the square root of a squared minus u squared means we use u equals a sine of theta, which is going to be the same as t equals 10 sine of theta. Okay, so our trig substitution, I'll just write TS for trig substitution. Here we're going to be doing u equals a sine of theta. So in this case we have t equals 10 sine of theta. So I cross out the one that says u because we're not doing a u substitution here, even though that's what it looks like in the formula sheet. Okay. So t equals 10 sine of theta. That's this one. All right, and then we go from there and we just try to figure everything out. So if t equals 10 sine of theta, then if we take the derivative of both sides of this equation, we get dt d theta equals 10 times cosine of theta. Okay. And then we can move the d theta over to the right side. So that's going to give us dt equals 10 cosine of theta d theta. Okay, so dt equals 10 cosine of theta d theta. And now we're ready to plug everything in up here and then work through the integral. Okay, so plugging into the integral, we have the integral of the square root of 10 squared minus 10 sine of theta quantity squared. Okay, and then instead of dt, now we have 10 cosine of theta d theta. Okay, so we have 10 cosine of theta d theta for our dt. All right, and then we can simplify this a bit. So if we look inside the integral, distributing the square, we actually get 10 squared is 100, so we have 100 minus 100 sine squared of theta inside of the square root. And then if we factor out 100 and split up the square root into two parts, we're going to have the square root of 100 times the square root of 1 minus sine squared of theta. Okay, so we have the integral of the square root of 100 times the square root of 1 minus sine squared of theta times 10 cosine of theta d theta. Okay, and then where do we go from here? Well, square root of 100 is 10. So this right here is just 10. And then we have another 10 over here. So 10 times 10 is 100, which is a constant that we bring out front. So we have 100 out front times the integral of the square root of 1 minus sine squared. Now remember, 1 minus sine squared is actually the same as cosine squared. So if you look on your trig identities, on the second page, key trig identities, we know that sine squared plus cosine squared is 1, which means that 1 minus sine squared equals cosine squared. Okay, so this 1 minus sine squared is the same as cosine squared of theta. Okay, so we have the square root of cosine squared of theta. And then over here, we still have a cosine of theta d theta. Okay, so we have 100 times the integral of square root of cosine squared of theta times cosine of theta d theta. Now you got to be careful here. Remember that the square root of a square is the same as the absolute value. Okay, so what we have here is 100 times the integral of absolute value of cosine of theta times cosine of theta d theta. So what do we do with this? Well, in particular, what are we supposed to do with the absolute value? Well, just like before, because we're talking about a right triangle here, and theta has to be between negative pi over 2 to pi over 2, cosine of theta is greater than 0 on that interval. Okay? So, cosine of theta is greater than 0 on the interval negative pi over 2, comma, pi over 2. Which means that we don't actually need the absolute value here. Okay, so I can just cross out the absolute value. And so I just get cosine of theta times cosine of theta, which is cosine squared of theta. Okay, so we have 100 times the integral of cosine squared of theta d theta. Okay, and then how do we integrate something like this? Well, you may have seen things like this in Calculus 1, hopefully you did, but you might not remember how to do them. Usually when you just have a single power of cosine or sine, often the best way to do it is to do a trigonometric identity. Because you can't really do a U substitution here, and doing it by parts probably wouldn't help that much, and it'd be a lot of extra work. So we want to use a trigonometric identity for cosine squared of theta. So we look on our trig identities, and we see this one right here. Cosine squared of theta equals 1 plus cosine of 2 theta over 2. So we're going to be using that one. Okay, so we have 1 plus cosine of 2 theta all over 2. Now, why am I choosing to use that one? Well, because I know it's easy to integrate cosine of 2 theta with U substitution, but you can't integrate the integral of cosine squared of theta d theta the way it's written. It just won't work. You can try U substitution all you want, it won't work. Okay? Alright, so but now we can just split up the integral into two parts. So we've got, if we distribute this 1/2 to each denominator, we're going to, or actually, let's bring the 1/2 out front. Sorry. So if we bring the 1/2 out front, we have 100 over 2 out front. Okay. Sorry, I was having a little brain fart there. Let me write this out. So we've got 100 over 2 out front, and then we have the integral of 1 plus cosine of 2 theta d theta. Okay, and 100 divided by 2 is 5. What? I really am having a brain fart. 100 divided by 2 is 50. Whew, that was hard math. Okay, so we have 50 here. And then what's the integral of 1 d theta? The integral of d theta is just theta. So we have 50 times theta. And then what's the integral of cosine of 2 theta? Well, the antiderivative of cosine is actually going to be positive sine because the derivative of positive sine is cosine. Okay? So here we're going to have positive sine of 2 theta. And then remember, if you're doing a u substitution and you just have a constant on the inside of your function, you end up dividing by that constant. So here we're going to end up dividing by 2. Okay? So we have sine of 2 theta divided by 2. All right? And then for this integral, it was an indefinite integral, so we're going to write plus c at the end. Okay, but you're not done. So now for the somewhat tricky part. So I think what I'm going to do here is I'm going to go ahead and leave it in this format, and then we need to probably draw a right triangle to be able to do the rest of the problem. So let's start with theta. So we need to plug in an expression in terms of the original variable t. Okay? So plug in expressions involving the original variable. And here the original variable was t. My t sometimes looks like a plus sign. I probably should work on that. Okay, plug in expressions involving t. So let's start with the theta here. How are we going to work with the theta? Well, we can do kind of the same thing we did on the last one. We might not even need a right triangle for the theta. So if we go back to our original trig substitution, we said t equals 10 sine of theta. Okay, so if we work with this one here, if we divide both sides by 10, we get t over 10 equals sine of theta. And then if I apply sine inverse to both sides, I get theta equals sine inverse of t over 10. Sine inverse of t over 10. Okay. And let me just check to make sure I'm in the right part here. Yeah, we're good. Okay. All right, so theta equals sine inverse of t over 10. So for that one, you don't actually have to draw a right triangle yet. And I think I'm going to go ahead and distribute this 50 here to each term. So we have 50 times sine inverse of t over 10. Okay. And then for the second term, the 50 and the 2 are going to cancel. And we're going to have 25 times, well, 25 times, right now we're going to have sine of 2 theta. So we need to plug in something for sine of 2 theta involving t. Now that's a little bit tricky, and if you want to do that without a right triangle, it can be even trickier. So if I look back at the original trig substitution, we might be able to pull it off. So we do know that sine of theta is equal to t over 10. Okay, so we do know that. So how could we get sine of 2 theta? Well, there's a couple ways we could do it. Probably the best way would be with identities. So we want, in blue here, we want to find sine of 2 theta. But we actually just have sine of theta here. This is just sine of theta. So if we look at our trig identities for sine of 2 theta, sine of 2 theta is 2 times sine of theta cosine of theta. 2 times sine of theta cosine of theta. The thing is, we don't know cosine of theta. So that's what's going to make it trickier. So we do know that sine of theta is t over 10. Okay. So we can plug that in here. But we don't know cosine of theta yet. That's the tricky part. Okay, so what we've got here is 2 times t over 10, because t over 10 is the same as sine of theta, right? But then we need to plug something in for cosine of theta. And the thing is, we don't really have an expression for cosine of theta. This one over here has a dt and a d theta. We can't have that in our answer. So what we're going to have to do is get a little bit creative and probably have to draw a right triangle here. So what we do is we start with the original expression here. Sine of theta equals t over 10. Okay? And remember, from SOHCAHTOA, the sine of theta is SO, which is opposite over hypotenuse. So here we have opposite is going to be t. And then over hypotenuse, hypotenuse is going to be 10. So if I just sketch a right triangle, that's probably the easiest way to find cosine. Okay, so here's our theta. And then the opposite is t. And the hypotenuse is 10. And then what we want is cosine of theta so that we can figure out what this is. So let's figure out cosine of theta. Well, we know that cosine of theta is equal to adjacent over hypotenuse. Adjacent over hypotenuse. And here the adjacent has to be this side here, which we don't know. But if you use the Pythagorean theorem, you know that this squared plus that squared is 10 squared. Okay? So the adjacent squared plus t squared equals 10 squared. So if we call this adjacent, if we call it, I don't even know what to call it. I'll just call it adjacent so we know what it is. We know from the Pythagorean theorem, that a squared plus b squared equals c squared. So we have adjacent squared plus t squared equals 10 squared. Okay, and we don't know the adjacent, but we can solve this for the adjacent. Okay, so if we subtract t squared from both sides, so minus t squared from both sides, then we're going to get adjacent squared equals 100 minus t squared, because 10 squared is 100. And then taking the square root, we get adjacent equals plus minus square root of 100 minus t squared. Okay, and then the real question is, do we do the plus or the minus, right? How do we know which one to do? Well, I would say because it's a right triangle, and because it's a triangle, you can't have sides that are negative. It wouldn't make sense. Because the side of a triangle is a distance, and distance can never be negative. So we're going to circle the plus. Okay, so we have positive square root of 100 minus t squared. All right, so now we're ready to calculate cosine. Okay, so we have cosine of theta equals adjacent over hypotenuse, which is going to be the square root of 100 minus t squared. So that's this right here, what we got for adjacent. Square root of 100 minus t squared over hypotenuse. And for the hypotenuse, we said that that was 10. Okay, so we have the square root of 100 minus t squared over 10 for cosine. Whew, this one's a lot of work. Okay, so there we've got our cosine, and now we can plug that back in up here into the formula for sine of 2 theta. Okay, so sine of 2 theta is going to equal, we said 2 times t over 10 times cosine. So plugging in for cosine here, we're going to be plugging in this that we just got. Plug that in right there. So we have times the square root of 100 minus t squared all over 10. Okay, square root of 100 minus t squared all over 10. Okay, and then remember when you're multiplying fractions, you multiply straight across. So we can simplify this sine of 2 theta. So in the numerator we have 2t times the square root of 100 minus t squared all over 10 times 10 is 100. And then we can divide the top and the bottom by 2. Okay. After we do that, we're going to have a 50 in the denominator. All right, so we get sine of 2 theta equals, we're going to write it the same way they do on my math lab, so t over 50 times the square root of 100 minus t squared. So there's our sine of 2 theta. That was a lot of work, wasn't it? Okay, so we're now going to plug that in, this whole expression here, in for sine of 2 theta, and then we're going to have our answer. So over here, this sine of 2 theta, we're going to go ahead and replace that with what we just got. So we're plugging in t over 50 times the square root of 100 minus t squared. Okay, so t over 50 times the square root of 100 minus t squared. Is that right? That's what I just wrote, isn't it? T over 50 times the square root of 100 minus t squared. Yep. And then the rest of this we already calculated. So don't forget there's still a 25 here. So we still have a 25 right there. Okay, so we have 50 sine inverse of t over 10 plus 25 times t over 50 square root of 100 minus t squared plus c. Okay, and then we can cross out this 25 and 50. So if we divide the top and the bottom by 25, we're going to be left with a 2 on the bottom. Okay, so we have 50 sine inverse of t over 10 plus t over 2, right, because there's still a 2 left over on the bottom, times the square root of 100 minus t squared plus c. All right, and then that whole thing there is our final answer, which was quite a lot of work. That's why I say this is a challenging topic, and that's why this week we only have 5 problems in this homework. Because as you can see, I did 3 problems that are similar to your homework problems, and it took me 1 hour and 18 minutes to explain everything. So that's quite a lot. All right, well, that's everything. Thanks for watching. I hope you enjoy your homework. Hopefully this will help a lot with that.